You see a job posting for an AI engineer with a median salary of $140,000. Immediately, you might think you need to relearn advanced calculus, read dense research papers, or go back to school for a PhD. You don't. An AI engineer rarely builds new models from scratch. The job is entirely different. Companies already have highly capable AI models. What they need is someone who can take that fragile, unpredictable model, connect it to their systems, and make it bulletproof in production. Over the next 5 minutes, we are going to do exactly that. We will take a chaotic large language model and wrap it into a resilient, crash-proof API that outputs perfect data and handles its own errors automatically. To build this, you only need standard software engineering fundamentals. If you can deploy an API, handle system errors, and use Docker, you already have the foundation required to execute this build. A perfectly trained, highly intelligent model is entirely useless if the software architecture underneath it crashes the moment something goes wrong. AI doesn't fix a weak system, it magnifies its flaws. Step 1 happens before we write any code. We have to map out the model's limitations by deliberately trying to break it in a playground environment. We start by running the exact same prompt over and over again, pushing the temperature slider to maximum. We need to observe the precise moment when the model stops giving predictable responses and starts spitting out complete randomness. Next, we deliberately overload the context window. We paste massive blocks of text into the prompt until the system finally chokes and fails. By doing this, you learn to treat the AI model's API exactly like an unreliable third-party payment gateway. You cannot trust it to respond quickly, and you cannot trust it to respond correctly every single time. Building an intuition for how and when an AI fails in a safe playground saves you hours of catastrophic debugging when the model misbehaves in a live production environment. Now we move to the code. We establish our basic API call, connecting our local software directly to the AI provider. This diagram shows what happens if you assume the AI will give you an instant response. It is a fatal architectural flaw. If the model lags, your primary application node will freeze and turn red while it waits endlessly for a response, taking down your entire application. To prevent this, we implement a strict timeout limit. If the model takes longer than 5 seconds to respond, we force a deliberate failure, severing the connection so the host application remains unlocked and active. Once the timeout triggers, we execute a retry loop with exponential backoff. The system automatically tries calling the model again after 1 second, then 2 seconds, then 4 seconds. This handles temporary network drops or rate limits seamlessly without alerting the user. If all of those retries are exhausted and the model still fails, we deploy a hard-coded, safe fallback response that we defined in advance. The user gets a clean error message, not a system crash. Treating the AI as a hostile dependency guarantees that your core software will survive any external AI outage. The next major failure point is the text generation itself. Often, an AI model will return conversational junk formatting, like saying, "Sure, here is your data," instead of giving you usable, parsable code. We fix this by integrating data validation libraries. If you write in Python, you use Pydantic. If you write in TypeScript, you use Zod. Look at this side-by-side comparison. These libraries strip away the conversational filler on the left and force the LLM to output a strict, predefined JSON schema on the right. Not most of the time, but every single time. Because the structure is so rigid, you have to treat your text prompts exactly like application code. They must be placed under version control, and they require test cases to track modifications. If slightly changing a single word in your prompt breaks the final output format, your endpoint is not ready for production. Locking down the output structure ensures that the LLM functions as a standard, predictable data pipeline within your application. To prove the endpoint actually works, we introduce a golden test set. This is our automated validation step. This data grid shows an array of fixed question and answer pairs being fed into our API block. We use this to automatically score the endpoint against edge cases again and again to ensure formatting stability. While testing, we meticulously track the request latency and error rates every day. We also aggressively cache successful responses, so the exact same question never hits the model twice. Identical questions often account for a significant portion of user traffic. Caching those responses prevents the model from processing the same request repeatedly, which can reduce a company's total inference bill by 30%. An AI system proves it is production ready only when its low latency, high accuracy, and optimized costs are tracked on a daily dashboard. Now, we initiate a final stress test on our new endpoint by simulating a complete, catastrophic network disconnect. The connection breaks, but the application doesn't freeze. The endpoint exhausts its retry backoffs, elegantly bypasses the error, and returns our predefined fallback response. By building around the AI's flaws rather than ignoring them, you have moved from writing experimental code to deploying production-grade systems. This technical transition is what defines an AI engineer in 2026. The foundation is set. The next step is scaling this resilient architecture to handle retrieval-augmented generation so your model can read private company data, or deploying agentic tool calling to let it take independent actions. Make sure you subscribe because we are covering that exact build in the next video.